If you walk outside right now, your eyes will tell you a very convincing lie. They'll say the Earth is completely flat. And from a biological perspective, your eyes are doing exactly what they're supposed to do. Because you are so small relative to the planet, you are experiencing something called local flatness. There is a strict mathematical limit to human vision. Standing on a beach at sea level, looking straight out over the water, the limit of your sightline is only about 3 miles. At that specific distance, the ground physically curves away, dropping completely out of sight. People noticed this physical drop-off long before we had modern science. Ancient sailors on those same beaches watched departing ships disappear hull first over the water, leaving only the tops of the masts visible before vanishing entirely. This visual quirk points toward a reality much larger than our immediate surroundings. Proving the planet's true shape doesn't require a rocket. It just requires a change in altitude. Thousands of years before we figured out how to fly, we realized we could use geometry and sunlight to artificially pull our perspective upward. This diagram shows the logic behind an ancient experiment by the Greek scholar Eratosthenes. He measured shadows cast by 2 vertical sticks in distant cities at the exact same time of day. Because parallel rays of the sun hit the curved ground at different angles, the resulting shadows had distinctly different lengths. By extending those angle lines deep underground until they intersected, Eratosthenes could calculate the degree of curvature between the 2 cities. From there, he successfully calculated the entire 360-degree circumference of the Earth, getting within a few percentage points of the exact modern measurement. Human intelligence successfully mapped the entire sphere millennia before a human eye would ever get high enough to physically confirm it. Today, we can make that physical climb, and one of the easiest places to do it is Dubai, home to the Burj Khalifa, a building that stretches over half a mile into the sky. When the sun sets on a spherical planet, the light doesn't just turn off everywhere at once. The shadow of the Earth's curve sweeps steadily from the ground upward. This creates a unique opportunity. If you watch the sun dip completely below the horizon while standing on the ground floor of the Burj Khalifa, you can immediately sprint into one of its high-speed elevators and ride it straight up to the 148th floor. That rapid 2,700-foot vertical jump raises your line of sight so high that you literally look over the curve of the Earth. Stepping out onto the observation deck, you get to watch the exact same sun set a second time. By using extreme architecture, we can artificially expand our horizon and literally outclimb the shadow of our own planet. To push the horizon out even further, we have to take to the air. But if you look out the window of a standard commercial flight at 35,000 feet, your view is usually obscured by heavy cloud cover and the narrow, restricted angle of the passenger cabin. You need an aircraft specifically built to reach the upper limits of the atmosphere, like the Cessna Citation X+, which can operate at a ceiling of 51,000 feet. Up here, the horizon is pushed back an astonishing 270 miles. With an expansive, unobstructed view from the cockpit, the distinct curve of the oblate spheroid is plainly visible to the unaided human eye. Altitude also gives us the ability to manipulate our relationship with time. When the supersonic Concorde jet took off from London near sunset, it flew westward so fast that it outran the Earth's rotation. Passengers looking out the window actually watched the sun rise in the west. High-altitude flight proves our geometry, and pushing the limits of speed proves the physical mechanics of our rotation. When we leave the atmosphere completely and move into orbit, the spherical model becomes an absolute requirement for our modern technological grid to function. This 3D wireframe shows GPS satellites orbiting the planet. Your phone finds its location because these satellites triangulate intersecting signals across a curved geometric plane. If you mapped this exact coordinate system onto a flat surface, the math would instantly collapse. We can also verify the geometry of the Earth by looking deep into space, specifically by observing the shadow we cast on the moon during a lunar eclipse. As you can see in this sequence, the Earth's shadow creeping across the lunar surface is always a perfect, uniform circle. If the Earth were a flat disk, its shadow would stretch into an oval, depending on the angle of its rotation. But a sphere is the only shape that casts a perfect circular shadow from every possible direction. From an orbital perspective, the sphere ceases to be a theoretical model. It is a daily, operational reality. Let's bring it back down to the ground. When you step outside tomorrow, the streets, lakes, and fields around you will still look completely flat. We now recognize the horizon as an optical boundary, an invisible line defined by the specific limits of our current vantage point. Empirical science is the tool we use to break past those biological limits. Human eyes evolved to navigate a flat, stationary plane, but human curiosity gave us the math, the architecture, and the engines to prove we are actually standing on a rotating mass hurtling through a vast solar system. You don't need to leave the planet to understand its true shape. You just need to be willing to elevate your perspectives,